Black Hat conference? Yep. The Black Hat conference. Yeah. And they open sourced code that can hack USB drives. All right. So you can infect any USB-based system. All right. So, I mean, now you're talking your phones when you charge them, your cameras. I mean, anything that's got a USB on it is a potential. So I'm looking at my USB and I think I'm just going to stay home, use my one secure computer, send everything up to Blackboard, and then just download it from Blackboard to here, because you got a major issue with all this USB stuff going on. So I sent you. It was a story that it came out on the British Broadcasting Corporation yesterday, but I think they sent the code out like late August, so it's out there. It's open source. So I didn't get a chance to look at it yet, but it's so beware. All right. So I sent you the link for that. I sent you another link there too. Let me just. Why don't you let me go to it?
Do you know much about how that code works?
I haven't looked at it yet. I haven't. But what it does, I mean, what you're learning here is what we call firmware. There is software that you can write for algorithms like you're doing in signal processing and all that stuff. And then there's hardware, you know, LEDs, motors, USB drives, all that kind of stuff. You're writing code that's firmware that has the hardware talking to software. That's what we call firmware, all right? And that's what these guys have done. They've actually, there's a way that they can maliciously hack into the firmware that's in Flash. So that's what they're doing. They're actually getting at the Flash in the device, from my understanding, and rewriting that code, all right? Or putting in their own code or something's going on there. I haven't seen it, but I would like to. I'll get a chance maybe tomorrow to get a look at it. I also sent you another one. This one is it's a nice little kit. I bought it. It's for $44. I can show it to you if anybody's interested. It is it's called the Butterfly Carrier Board. It's an extension that goes onto the Butterfly board. It has some nice little features in it. There's some sensors, some peripheral circuitry. What this allows you to do is to do RS-232 programming also. So when you leave here and you don't have your $60 JTAG programmer, you can program through RS-232. All right. It was $44 with the Butterfly board. I think it's like 20-something without it, but that's the link for it. And this is the board itself. Here's your Butterfly board. They give you a whole bunch of stuff for the Butterfly board, but you have all the headers there. But they give you the DB9 connector. That goes for your RS-232 port. This is how you populate that board that they have for you. All right. So look, I'm going to kick the tires on this thing, so I'll let you know. You know how it's going to go, all right? But it looked interesting. It wasn't that expensive, so I put the link up there for you to look at, and I'll find some code or write some code to ring the tire, you know, ring this thing out a little bit, okay? All right. Any questions so far? Are we all right? Somebody, where's O'Malley? Bill, you asked me something about double stack.
Yeah.
What? I don't know what you mean by double stack.
The most recent lab we just did, I was trying to figure out a way to make it so it was just a series of function calls, but for each function we had to redeclare the stack. Like the one thing we wanted that
What do you mean redeclare the stack?
like we wanted the stack pointer at 1D9 for one of them.
Okay.
And then for the other one I think we wanted it RAM N or something like that, but I wanted to figure out if
Oh, for the lab, in the lab.
Yeah.
Yeah, okay.
I wanted to know if there was some way if I could do like call activity 1, call activity 2, call activity 3, while still being able to redeclare the stack pointer for the purposes of each lab, and then still somehow go back and.
Well, so you have a series of call statements then, right?
Yeah.
All right, so let's just assume you start all the way at RAM end. Okay, that's the default, where the stack pointer is, all the way at the end, right?
Yeah.
So then I do a call, it pushes that address, the return address, onto the stack. I do another call onto the stack. Now, are you doing something inside the subroutines?
Yeah.
All right. Are you pushing or popping or calling or?
It was for the, it was both. We had to push, we had to redeclare the stack pointer, 0x1D9, or 190, and then, push and pop values off of that. I want to know how I would kind of get it back to where it was supposed to be after all of that, to, return to the main.
Well, you can set the stack pointer anytime you want. I mean, you want to redefine the stack pointer where it is?
Yeah, is there any,
It's the two registers. It's SPL and SPH. You can write right to them.
oh, so you have to redo that whole thing every single time you want to repair. I didn't know if there was some way to just to do it real quick back in a single command or something.
You can write to the stack pointer anytime you want. SPL equals, like, you can do, I mean, here. Hold tight, hold tight. Talk to the hand, talk to the hand. Let me go back.
Puts the address of the next command into the stack.
That's what goes onto the stack, right?
Your subroutine, as long as you pop off what you push.
It's gonna be fine. Whatever, when you're inside a subroutine, if you're pushing, the number of pushes you have, the number of pops you have to have, so it gets the stack pointer back to the right place, so you get the return address of the next instruction.
Yeah.
Yeah,
Oh, for that one activity, you only push, and you don't pop anything off in the one
yeah.
activity. So that's probably where the problem is.
So then what you would have to do is you would have to know where that address is that you want to get back to, and then you can set the stack pointer either to it or SPL and SPH. The last of your special function registers are the status register, right? And then right before that is either SPL or SPH, and right before that is SPL or SPH. So you can define them anytime you want. It's usually not good to play around with it unless you really have to, because it's going to do it for you. As long as, but I don't see why you would have a push without a pop in a subroutine.
Yeah, we did have both.
Okay.
Well, what I asked him technically, he's trying to write multiple activities in one program. They aren't really worded to do that under one program, but you have to do extra steps. Like he was saying, you got all those things that say push, you got to pop them off. But the codes, the activities aren't written expecting us to write them in the same code, right? They're expected to be done in separate programs, right?
Yeah.
Okay, exactly.
Yeah.
That's why.
Yeah.
I have a question. You said the stack automatically is set to RAM end.
Depends on where you.
So it's not defaulted.
No.
Because you
Well,
have to do initially.
usually it does. I force it to go to RAM end.
Right, but
Yeah.
if it's like you're just resetting it, then you can't even write anything into the stack unless you initialize it. You have to initialize it somewhere because it can.
You can't decrement. It starts at 0. You can't decrement from 0. Then you push something off.
So it defaults to the stack pointer starts at 0.
Yeah.
Start up.
Hold on, I just started it up. Let me grab a piece of code. Let me just grab something here. Let's see. Let me get the example I was going to do anyway.
You have to add it to GPR. I don't even. You can't do like common drafts, right? Port B is this one.
All right, so I got the simulator up, good. We're going to build this. I'll run, I mean, this is the code I wanted to go through today anyway, but, all right, so I build it, and now I'm running this, okay, yeah. Yeah, it looks like it does start there, yeah. So typically what you want to do is I will set up SPL and SPH here.
And if you try to put something on right away, would it actually do the opposite and increment it?
We could try it,
Nah,
you know.
There's no complaints.
Yeah, you can't decrement below SRAM. You know, there's just no, it's not physically there.
Is that stack pointer 0, register 0?
What do you mean? Here's the stack pointer.
Right,
Stack pointer's pointing to a memory location in SRAM. I mean, all right, let me go. See, that's the beauty of having my flash drive here with all my other stuff. Let's see. Where did I do that stuff? Jumps, loops, calls. All right, let's see. Oh, there we are. Initializing the stack pointer. Yeah. Yeah, right here. We'll get to, yeah, it's a directive. All right, hold on. Let me answer your question. Is this what you were talking about here? That's to initialize, because what this will do, it'll go into the include file. So any, if I have a 169p, a 2560, a 32, whatever, when I include that inside that include is all of where this stuff is. I think it's one. I'd have to look it up. But each one of these are defined in there, so I don't have to memorize what they are. This will automatically grab what that is, the high part of it, because again, it's a 16-bit 16-bit address, and this will out it to the high pointer, out it to the low pointer, and then my stack pointer will be set at that point for anyone. Right? Yeah.
I have another question from the homework.
Okay. Well, somebody else had a question first. Somebody have their hand up? No? Okay.
One of the questions asks, is the instruction COM port B a valid instruction?
Complementing port B,
Using the COM instruction?
I think you can only.
Because wouldn't you have to out it again, port B?
What are you trying? It says.
It just says, like, is the instruction COM port B a valid instruction?
I don't. I think you have to just take it to a general purpose register and then
Okay.
complement it.
That makes sense.
Yeah. You could. Comming port B would be doing a hardware. Yeah, I think yeah. Yeah, you would have to have that inside a general purpose register first, and then you can, if you want to complement it, read it in, complement it, and write it back out. Mm-hmm. That's the route I would go. All right. All right, so I'll let you know about this little handy dandy piece of hardware and. So you did the LED labs, right? That was okay?
Not yet.
Well, you guys, the Thursday group's tomorrow, but the Tuesday group, you're good? Jake?
I had a problem. I went on the PowerPoint to copy your 1 second delay
Okay.
example, and it wouldn't run on my computer. Every time, I would put a breakpoint somewhere, and I click run after the delay,
Were you simulating or doing it in the hardware?
simulated, and it just every time it would wait for about a minute, and then come up and say, "Do you want to keep waiting or cancel?" I didn't know if it was my computer.
It was just taking a really long time to run all the cycles necessary to make it a million microseconds.
You weren't single stepping through it, were you? You were F5ing? Yeah.
Yeah,
And it wouldn't go to the breakpoint?
no,
Mine would rather just take
it might have. I just
I don't know. I ran it in the hardware and I was getting 1 second delay because you saw the LEDs were going on and off at a second.
maybe I'll bring my laptop and then.
Yeah, the best thing is if you could show it to me, and I could probably do something with it. Yeah.
I just have a question here. Do you prefer for us to use the code that you have that counts and divides by 256 and has an outer loop and inner loop? Do you know what I'm talking about? You have this code in your PowerPoint that.
That was for the speaker? Was that?
That was for the speaker.
Yeah, I didn't go over that yet, but I wanted to wait until we got to pulse width modulation. That's why I really don't worry about that. You're not responsible for that. That code was just to test your butterfly board.
Oh, right.
That's all we wanted to do. I will get to, when I get the pulse width modulation, we'll revisit that. All right? Yeah. Okay? Okay. All right. Good questions. Good questions.
Don't forget to save us.
Don't forget, yeah. And it was interesting. I took a webinar yesterday, and it was about this flipped classroom concept, and I'm really going to try to push it in here. All right, I think it's something that, huh? Yeah. Well, it's something where you have to be responsible for coming in and being ready, because you're going to be working in groups, and your group's going to want you to be ready. So there'll be, you know.
I'll make a promise if
Yeah.
my labs can be less than 40 pages.
All right, you're all good. You're okay with it. As long as the labs are, the write-ups are shorter. But it's going to take a lot of front-end stuff on my end, all right, to get all this set up. So just bear with me, all right? But I kind of did it last semester when we started going over here when doing our hardware projects. But especially when we get to the hardware stuff, you got to be ready. You can't come in and just start reading the stuff and figuring out what the hardware is going to do. So you got to really be set there. All right. All right. So back to math and okay. All right. We left off here the other day with basically the compare instructions, which are all the branching, branching greater than, less than, equal to, and all that. And there was an example I wanted to do is assume port B is connected to a temperature sensor that basically it's an 8-bit temperature sensor that's attached to port B, and write a program to read the temperature and test the value for 75. And basically, if the temperature is equal to 75, then make R16 equal to that temperature value and force R17 and R18 to be 0. If it's greater than 75, make R16 0, R17 equal to the temperature, and R18 0. And then if it's less than, just flip it around and have R18 where that temperature is. So it's just using an example of what we just talked about, and that's what I have loaded up in Atmel Studio here. Now, again, when you're even in lab or whatever, you always have to give yourself some kind of data, So I physically here I'm simulating a port. So what I have to do is I have to initialize that port to something, so I have some kind of data there that I can read in. So here's what I did. I set up, first I'm going to set up I'm going to make port, now again, port B is where you're reading it in. So what I do is in order to get data to port B, I have to write some data out to it. All right? So here I'm just going to write out to, can you guys see this in the back? All right? All right. So, so here we're just going to set up the data direction register for port B to be an output. And then here I'm just going to simulate a temperature of 70 degrees. That's all. I'm just simulating a simple 70 degree. All right, and then I output that to port B. Then I load up the R20 with 0 zeros, and then I output that. So now that makes port B was an output because I've written something to it. Now I'm making it an input. Okay? And then I'm just going to clear these registers here. Then we'll take in to R20 the contents of port B. And, well, let's run it. That's why we're here. All right, so we're going to set up. Let's look at the I/O view first. And we'll get to port B. So here we just written out to it. And you will notice again, that it went from red to blue. All right. Nothing has changed, all right? Nothing has changed here. These bits are still high, okay? It's just the only time you'll get a red one was when it's changed on that last command, okay? So here we're going to out it. So here's the 7-0 that's written out to it, which is going to give us a 4-6 hex, okay? And now we're going to make the data direction. Now you notice that the data direction register was forced down to all zeros. We forced it to be an input. Here's my pins here that are all set up with that one thing there. And then we just clear off these registers. And now we're going to compare immediate. We're going to do an immediate compare here. All right, so it's going to do a subtraction. All right, so now we're going to branch high if it's above, all right? Obviously, it's not high. And then we just get down to the end here. And then we'll see if we go to our processor view. there sitting in R18 because it was below 70, all right? So that was just using that compare instruction, okay? All right, everybody all right? So it's just an example to compare stuff. We just went through all that.
BRSH, it branches if it's equal to or
Higher, yeah. Yeah. All right, and here what we're going to do is just, we're going to add two signed numbers in R21 and 22. Store the result. If it's not correct, the program should output an A to port A. All right. So now we're going to test. We're going to be testing the overflow flag. All right. So we want to test the overflow flag here. So here we just set up. So here I'm going to have the two numbers, which is going to be FA and 05. I'm going to set up the port A to be an output port. Add the two numbers together. And here's where we're going to do our test on the overflow flag. So you branch on if the overflow flag is clear. So if V is equal to 0, then we're going to go to next, which was what we bail out. If not, we just load up the thing to port A, and we're going to send something out to port A just to alert the user that you've got an overflow problem there. All right. Rotate instructions. These are very useful when you're doing serial communications and stuff, doing things like checksumming and things like that. Rotating is when you're doing serial communications like you have with a USB port, you're literally, and if you have an I2C or an SPI or whatever, you're basically sending it over a wire, all right? You can think of it as a serial communication. So the way we can do that is we can do this 8 bits at a time if we would like. My general purpose registers are 8 bits. Perfect for them to be used for this type of stuff. You'll set up like a pin on port C, pin number 7 or pin number 2 on port B. So you'll have physically a wire going from one place to another. So now all I do is I get a general purpose register with the 8 bits I want to send, and then just start writing it bit by bit to that port. Okay. Well, the nice way to do it is I can do it using these rotate functions, all right, rotating left, rotating right. It's just they give me a lot of flexibility. So what the rotate right does is you're effectively going to take the least significant bit, gets moved into the carry, and then the carry will get rotated around back into the most significant bit. So if I do a rotate right once, it's basically going to take, like here, in this example here, if I load a 2.6 in the R20, we then do a rotate right, so now you're going to shift everything gets shifted to the right. This bit here gets shifted into the carry, all right? And then the carry from back here gets rotated back into the most significant bit that you have all the way sitting at the left-hand side, okay? Rotate it again, now the carry bit's set to 1. That carry bit will then get moved into the most significant bit on the next way around. Same with rotate lefts, all right? You can rotate left. Here, you're just doing the opposite. You're taking the most significant bit, going into the carry, and then that carry bit gets rotated back into the least significant bit as you come down, okay?
Why are you clearing the carry bit and setting the carry bit if it only matters on what you load into the
Oh, I just for an example. Okay. Yeah, I mean, just to use it as an example. Typically, what you would do is you would clear it, all right, unless otherwise, Okay. But here, this is just for this example. I'm just setting it, just to show what's going on. No?
No, I'm just making sure.
Yeah. No, I'm not trying to play any game with you here. No. Yeah. Yeah. So if here I'm going to rotate left, I'm going to take the most significant bit. It's going to come out and go into the carry here. So if I set the thing here, and I start off with this, okay? When I rotate it, now remember the carry, this is wrong. I set the carry bit. The carry is 1. That should be a 1 on that slide. So now what's happened, the carry bit comes around and back into here, okay? And then the next bit will get rotated into the carry, which will be a 0, and then that comes back in, okay? So you just keep working your way around there. All right. So serialized data, it's a way of sending a byte of data one bit at a time through a single pin, all right? And that's what you have with your I2C stuff, all right? There are two ways to transfer the stuff serially. You can use the serial port. Programmers have very limited control over that, and we'll get to that when we get to Chapter 11. The second method is to transfer one bit at a time and control the sequence that you're doing, okay? And the spaces that are between each bit. Devices like liquid crystal displays, analog to digital converters, some versions of ROM. The serial versions are becoming extremely popular, okay? They take up less space on it. I mean, it takes up less real estate, which is a beautiful thing, all right? And now we'll use the rotate instruction to do it. So we're going to write a program that just takes an 8-bit number. We're going to send it one bit at a time through port B, pin 1, and we'll put a high bit at the beginning and at the end. So we're going to basically say, okay, a high bit, 8 bits of data, high bit, and then that's going to be just sending 1 byte of data. And you could obviously set this up to do as many as you want. Okay? All right, so typically, you know, it wouldn't be sunny without sung if you can't flow chart, so we're going to flow chart it. So first thing we're going to do is we're going to force that bit. I know. Oh, so sorry. All right. Bit 1 of port B is an output. All right, so we set that up. All right. Then we're going to let R20 is going to have the value, whatever we're going to do, and then we're going to clear the carry flag. Okay. All right, so we set up R16. Now again, we're only going to do 8 bits here, so we'll set up R16 to be an 8-bit counter. All right, so R16 is going to be the counter that we're going to have, and then bit 1 of port B is going to be set to 1 for a start bit. All right, so that's the start bit of our communication that we're going to do. All right, then we're going to we know we're going to have to loop through this 8 times, so I'm going to need a label where I have to loop back to. All right, so I loop back to this thing called again. All right, now I rotate right, and I'm going to send the least significant bit to the carry flag, okay? So I'm doing the rotate right, come down, and now we test if the carry flag is equal to a 1, then send a 1. All right, so if that is true, we then go up and we hit the label for a 1, so this is a label, and then I'm going to proceed to send a 1. When we're done sending the 1, my next label is going to be where I'm going to decrement the counter that I have for this label here. So I decrement the counter. I look and see if R16, where the counter is, if it's not 0, then I'm going to go back here to again. All right. So if that is true, I could jump back to again, and now I'm ready to send my next bit. Okay. All right, if we come down through here, and if it's a false for the carry bit is equal to a 0, then I'm simply just go to sending a 0. And once I'm done sending a 0, I'm going to head right back to my label here and then do a decrement. Okay, so then we just head right back over to there, come down through. We're going to test R16. So we're going to be looping in here 8 times until we get a false coming out of this test right there, and then we know we're done. Okay? I was at a department meeting the other day, Monday. It came up. Now, I'm not going to say who. The students don't know how to program loops. I said, wait a minute. I said, I'm programming loops in assembly language. Can you guys do loops? You can do loops. All right, good. So I'll let that person know. And I'll show them on the midterm that you can do loops. Oh, midterm, Monday. I won't be here Friday. I have a NASA thing I got to go to. Yeah. I have to go up to a little. Oh, it's Christmas early this year for you guys. I can have somebody proctor the exam on Friday. All right, democracy. All right, who wants a Friday? One. No, all right. Yeah, Anton. Homeworks. Homeworks in there's so much stuff on the slides in the homeworks. It's modified versions of that stuff. All right. It's really. Yeah. All right. So Friday, you do have to be here, because I have an in-class assignment for you. The son will be here, too. All right, so the code for this, we set that bit immediately to a 1 in the data direction register, because we're going to make bit 1 of port B an output. Now we load in, just taking it right off our flow chart, we load in the data that we're going to use into there. We clear the carry, clear our carry bit, because we're going to be rotating into the carry bit. So you asked earlier, why did you set it and why did you clear it? In this case, I want to clear it because I'm not ready to send any data yet. All right? So just to answer your question earlier. Then I'm going to, all right, so we set that guy up. Now we need, this is our start bit. So again, we're going to transmit a 1 before we send the data, and we're going to transmit a 1 after the data. So you've got 1, 1, 8 bits in between the 1, 1. Okay? Here's my again label. Here's where I'm going to come back to. So this is so at this point, I'm done setting up my start bit. All right? Now we rotate R20. All right? So we rotate on R20. Now we branch on a carry set. If the carry is set, that means the carry is equal to 1, then go to 1, which is send 1. All right? So this 1 label is going to be down further. So bit 1 of port B is cleared to 0. So this is setting it up. We jump to next, and that goes on. So 1 here, I'm right at this point. We've set it up for a 1. And up here, we have cleared port B, that pin. So this sends the 0. This sends the 1. We set the bit, or cleared the bit, and we set the bit, and we told it what port and what pin. Okay, so we're using pin number 1. And we go out, and then we simply, here's my decrementing, and I branch on a non-equal back to again. So this is going to loop it 8 times. So when I'm done, I have to send my stop bit. So my stop bit gets set here. I set the bit immediately on port B to a 1. Yes?
You know how there's that synchronizer delay when you set the pins of a port?
Synchronizer delay.
Yeah, there's like a clock cycle where it takes like a clock cycle to reach from the port to output to into the pin.
Okay.
Like there's a delay. And I was wondering if you ever have to worry about that when we're like programming the butterfly board, if that ever like becomes a serious problem. Because the book makes it seem like a big deal, like there's a whole section of it where chapter
4.
4.
Yeah.
But when I'm like, when I'm stepping through my programs, like it doesn't
When you're simulating it, I don't see it. That's a good point, though. Let me look at. Yeah.
like I just.
I mean, it's at most it would be like 1 clock
it's
cycle.
Just one clock.
Yeah.
So I don't
Yeah.
know if we ever have to worry.
That's just setting it up. Yeah.
The only way that would have an effect is if you're immediately checking something on the next line of instruction from the pin.
Yeah.
That's the only time it would have a place. So if you
Yeah.
do that,
Like you would have to set the pin, the port to be the input to do that.
yeah, that's what I'm saying. So that's the only
Yeah.
way it would affect something. So if you did have to do that, you just put the mill out there and then put those on.
Yeah. All right, here what we're going to do is we're going to read into pin number 7 and save it into a register, all right? So the byte comes into the least significant bit. So here we're going to clear the bit on the data direction register, pin number 7, so we're forcing that to be an input. Again, I'm going to do an 8-bit here. Load up R20, load immediately, R20 with a 0. Here's my again back here. So now I'm going to here, you're testing now. We're testing that bit. All right? So skip, right? The bit is clear. All right? So if the bit is clear, so if I'm reading in a 0, we're going to skip over this, and then it's going to skip if a bit is set. So if this skip if I have a 0 sitting on there, all right? If I have a 0 sitting on here, it's going to go down and test for a 1. Well, testing for a 1, all right? So if this is true, we're going to go down and move over. All you're doing here is you're alternating between setting the carry and clearing the carry and then doing the rotate here. So this rotate will move that carry flag to the most significant bit of R21. So we're just moving it in. Then we decrement R16, and then we branch on a non-equal right back again. So here we're testing here. It'll skip over this, all right, and then do the clear. And if that's true, it'll skip over it. So this effectively sets up the carry, and then I'm rotating that back into R20. So that's going to bring basically whatever you're reading on pin B, or on port C, pin 7, here's where I'm setting the carries, and I'm rotating them in to the register. All right, so it allows me to rotate those guys right in there. And then we just loop back again. Okay. All right, there's a logical shift left, which basically just starts clearing bits out. There's no rotation back into it. It's pretty straightforward. All you're doing is every time you do an LSL, it's just going to take. And what it does is it comes into the least significant bit, comes in a 0. All right? So if I do this 8 times, I'm going to have all zeros sitting in here. Okay. Again, they're giving you flexibility on how to work with your 8-bit registers. Okay. There's a logical shift right. So then you take the most zeros come into the most significant bit, the least significant bits go out to the carry. Okay. Arithmetic shift right, same thing. What you're doing is you're going to take whatever the most significant bit is, that's going to get just cycled back in. Everything gets shifted out to the carry bit. Okay. And here's an example of what you basically have there. All right. If you notice when I'm doing an arithmetic shift right, if I load into this register this guy, this thing, you're going to just logically, it's just going to do an arithmetic shift right. All right. Now, we have an in-class problem. I want you to read port B, set up port B to be 6-4 hex. Write the port B 6-4 hex, write a program that's going to then read the 6-4 hex into a general purpose register and then count the number of ones that are in that. Use 6-4 as an example. Or if you want to use any example you want. But right now, let's set up the port B, read something in, and place that count into another general purpose register. All right? So at most, you can have 8 bits being a 1, and at least 8 bits, they're all zeros. But here we're going to have 6-4, so you should have 3. Should be sitting in a register. You've got 0, 1, 1, 0, which gives me 2 high bits. 4 is 0, 1, 0, 0, 1 bit, so we should have a 3 sitting in there. Okay? And just to let you know, for Friday, please go back and look at, you're going to write a subroutine that's going to multiply 2 16-bit unsigned integers. All right? These are the 2 numbers you're going to multiply together. Anybody have any idea how big the result's going to be? When I'm multiplying, if I multiply 2 8-bit numbers, how big is the result? 16-bit. 2 16-bit numbers are going to give you a 32-bit result. Okay? Now remember, you have to have these partial products, and you have to accumulate the additions on those partial products. So that is to be handed in on Friday. Okay? We'll turn that in. Yep. There we go. Yeah. So first thing, set up port B to be an output, write to it, then read it back in. And now you read it into a general purpose register. You're going to need to set up 2 counters. One's going to be a loop counter that starts at 8, goes around, and another one's just going to be a counter to count the number of bits. Okay?
said 64 hex, right?
64 hex. So you should get 3, should be your answer, your final result. Let me know when you get it, all right? When somebody gets it, I want an email to me because I'm going to email to all my faculty saying they can do loops. Michael, what's up?
So, when it comes to counting the number of ones,
This is backwards, first of all. It's FF and R16 over here. That's not going to compile.
oh yeah, definitely.
Go ahead, you had a question?
Yeah, when it comes to counting the number of ones, are we using a specific instruction?
That's what we have to start thinking about, yeah. Think of it. Read them in. Move something into the carry. Do a rotate.
Then check for that.
If the carry is set, branch on carry set to add. If the carry's clear, don't add. You see what I'm saying? So you can do a logical shift left or a logical shift right, or you can do a rotate if you want, whatever. You just want to get that bit going into the carry. And then you're going to work on that carry. Branch on the carry set, branch on the carry clear. If the carry is set, what do? You have to increment a register, right? I have to increment a register and just, that's it. If the carry's clear, I don't do anything. I go back and check for the next one. Flow chart. Huh? 6-4.
Why do you put it into port D that Israel is?
Simulating you're reading something in. That's all.
Can't you just check it now?
You could. I just wanted you to simulate writing and reading to the port. Okay? That's all. Yeah, I mean, if you want to make it easy on yourself, just put something into a register and start counting the bits and then go back and just set up the port if you want. You know. There's 2 things going on here. You're doing a loop, you're testing a bit, and you're, 3 things, and you're setting up an I/O port as an input in it. All right?
Is this in the chapter 5?
What's that?
Is this going to be on the test when you get it?
All of chapter, well, not everything in chapter 5 except for packed and unpacked binary coded decimal.
Okay.
Yeah.
What's the command that checks the carry bit?
Branch on carry set, branch on carry clear. It's right in here. BRCS, it's right here. I summarized them right back on, right there. Oh, that's branch not equals. It's branch BCC, branch on carry clear, branch on carry set. For the exam, textbooks only. All right, if you have an electronic version, you can have that up. If you have the hard copy, you can have that in front of you. Yeah.
First, I put just 0 to text the number of the counter.
Yeah.
My counter is R22.
There you go. So it's going to be all zeros, right?
Yes, so 0.
Yeah.
So let me try to put FF. So
We'll get 8.
Yes.
If you just put a breakpoint down here and hit F5,
Okay.
yeah, put a breakpoint.
So I break point right in the loop.
At the end, right here. Yeah. Right there. No, right before it. Right there, yeah. And then if you just run it, and then hit F5, it'll cycle through the whole program. You know what I mean?
Yes.
All right, now we can look.
It's not working.
What are you doing? Well, you still have it at 0. Put it at FF, stop it. FF. You needed, I think you had to rebuild it,
Yes.
right?
No, it's working.
Oh, okay. What do you got now?
8.
8. All right, put in 6, 4. Six, 4.
I need to rebuild.
Huh?
I need to build again.
Oh.
8.
Ah! Did you get your Digilant thing yet?
Yeah, I got it right.
It's nice.
Yeah, I just got it today.
Yeah.
3? 6, 4, 3.
Yeah. 6 has 2 1s and 4 has, yeah. Good. Got 1 done. Got it. All right, did you run it with 6, 4?
Yeah, I got. I got.
Should be. All right. All right, one of you guys, just one of you emailed, Rachel emailed to me so I can send it on to my esteemed faculty